All right, horizontally projected motion, horizontally launched projectiles. So two balls of different mass fall from the same height at the same time. Which ball is going to hit the table first? Well, we know the answer is they hit the table at the same time. We know that mass doesn't matter. Mass is not going to matter until we get into Newton's laws, and that becomes a factor in our equations, right? But this is true only when we're in a vacuum, right? Because then mass does have some effect when we have air resistance. And we talked about that, and we talked about seeing things fall in the vacuum, and we saw the free fall videos where the computer simulation, we're going to add, at one point, we'll add in air resistance, and then you can see what effect does mass have when there is air resistance, or the shape. What happens if we make something have a bigger surface area, right? Obviously, this, I know you guys know surface area is going to affect, the rate at which things fall. That was the feather in the coin, or the bowling ball and the feather that we saw. But right now, mass, right, doesn't have any effect on the rate at which things fall or the time that they hit there. So it's independent of mass until we get into Newton's laws, and we don't really need to worry about the mass. So what we're looking at now is this situation where these things are moving down like this, but while they're moving down, they're also moving to the side. So right now it's moving in the negative y direction, but now we're going to make it move in the x direction at the same time. So here's the key. Everything that we learned in the free fall motion stuff still holds true. There's nothing new to teach you there. We're just going to combine it and review it while we're going through this, right? And so other types of motion exhibit this characteristic, and that's projectile motion. Right now, I'm not going to ask for a definition of a projectile, but you should know what these things are. There's some terminology that we haven't used before, like what is trajectory, right? Some of these things, what is range? You've probably heard of before, and maybe you haven't heard of them, right? But a projectile, here's the key with a projectile. It's an object that's projected by some external force. Normally in class, what I do is I make a paper airplane and I throw it around the classroom so you can see it float around and fall to the ground. It's a good projectile. But in order to make it go, I need to throw it. I need to exert a force. Here, my little bow and arrow guy has to use the bow, right? The force of the bow with the string exerts on the arrow to make it become a projectile. That's the external force. And so this idea of external force or outside force or unbalancing force is going to come into play in Newton's laws, which is our next unit after projectile motion. But we need that external force to cause the horizontal motion. But then after that, right, this guy's only launching the arrow here. He's not continually launching the arrow as it moves across the screen, right? It's like if you kick a soccer ball to your friend, you kick the soccer ball one time to make it start moving, but you're not continually kicking the soccer ball, right? And so it's just that initial external force that gives it the horizontal motion. It doesn't stay with it. But after that, we know that the force of gravity is going to pull it down, and then there's air resistance, but we're going to neglect air resistance always. So a projectile is anything that's been launched somehow by some external force, but now is only under the influence of gravity and air resistance, right? So I can't have an engine, an airplane with engines, a rocket that a plane is launched. Those are not projectiles until the engines stop working. So if you're in a plane and the engines stop, now that's a projectile because it doesn't have a way to control its own forward speed, right? Then it's just going to keep going forward because of the speed it had, but it's going to fall because of gravity. That would not be a projectile if it has engines. So now ask yourself this. Now my diagram, I meant to cover up what you see there, but my diagram kind of gives you a hint. And I've got a video of me doing this. And normally I would do this obviously live in the classroom. But to give you a little idea of what this contraption is, this is a little spring-loaded device. This ball right here can be, so imagine, see where this knob is. What I do is I pull this knob back and I put it in one of the notches. This is the spring back here. So when I pull it back, the spring compresses. And then what I do is I flick this up, then the spring uncompresses and exerts a force on the ball that we put right here, right? Which then gives it that external force to make it move this way, and then it's going to fall because of gravity. Now, when I slide this back to put it in the notch, this whole thing, this like little plunger thing, then extends over here. So what this ball has some holes in it, so it slides on this plunger, and I put it right here. So I have one ball right here, one ball right here. I pull this back, I flick it up, this slides. So then when it slides, this ball then falls straight down. This ball gets hit and goes out like this, right? And so the idea is what's going to happen, right? Well, this ball is going to free fall. This ball is going to free fall, but it's also going to move to the right at the same time. So the $1 million question is, which ball is going to hit the ground first, right? Now, the diagram kind of makes it look like, well, they probably are going to hit the ground at the same time. And if that's what you're thinking, whether it's because of the diagram or you're otherwise, you'd be correct, right? But the common misconception is people think, well, this ball is going to take longer because it's going farther, right? This path right here, you see this is a half a parabola that's upside down. It's a longer path than this, right? Or sometimes people think this ball is going to hit the ground first because you've hit it and you've given it a higher velocity than this ball to start with. But the key is their vertical velocities are exactly the same, right? This ball's not moving initially. This ball's not moving vertically initially at all because this is horizontal, right? And vertical is y. And so the fact that we give it an external horizontal force does not affect the vertical force or the vertical motion. And so this was from a couple years ago. I had a student video me. This is the little contraption. It's in slow motion. It's in notch number 1. And you'll see one ball will hit right here and one ball is going to hit right over here. Right, you can see it moving and you can see it moving, right? And they hit the ground at the same time. Now here what I do is I put it in the second notch, right? So now that I compress the spring more, which means it's going to hit the one ball harder. It's going to make it go faster. It's going to make it go farther. It's going to make it land farther over here because I put it in a bigger notch. It gives it more energy, a bigger force. But, so then the question would be, is it still going to hit the ground at the same time? Well, the answer is yes. It's still going to hit the ground at the same time. Whoops, sorry. This one's a lot slower for whatever reason when the student videoed it for me. So it's going to land like right over here, but you can see that, right, it goes out of view a little bit, but you can tell that they are tracking each other vertically. It's just that one is moving horizontally at the same time. And this is what you would see if we could take, I don't know what you call that photography. I always call it strobe photography, but I believe that's not the correct thing. When you take, you put it on like rapid fire. So it's taking lots of pictures over and over and over again for, the cameras do that, probably do a lot more than that. But if we were able to do that, this is what we would see. The ball that falls straight down, right? We see that the distance between the red ball here is getting a little bit bigger each time. It is for the yellow ball also vertically. But if we were to add some lines here, you would see horizontally, it's moving the same every time. But the idea is here, if you look straight across, the red ball and the yellow, I think that's yellow, are about in the exact same vertical position every time. And so this is the key. Horizontal and vertical motions are independent of each other. If you make something go in the X direction, that does not affect its Y motion. As long as things are perpendicular, they don't affect each other. Now, they combine to make a resultant, though, right? And so that's going to be a little bit new. I know we've talked about resultant a little bit. And so while they don't affect each other, they do combine to make a new result. The red ball's falling vertically. The yellow ball's also moving vertically, but it was launched to the right. And so the key is you see they track each other vertically step for step, and that's why they still hit the ground at the same time, right? And students, right? For one way or the other, we'll go with, the red ball or the yellow ball hitting first, because either the yellow ball has a shorter path or a longer path, but it has a greater velocity, or the red ball has the shorter path, so it's not traveling as far. But the idea is they're traveling the same vertical distance. And we know that all things fall the same in a vacuum. Now, so then the next question becomes, right, what do we do? Can I make it fired, the one that I fire horizontally, can I make it fired so fast that it will hit the ground before the one that free falls, right? And the answer is no. The only way that's going to happen is if I launch it so fast that it leaves the Earth's atmosphere and goes into orbit, right? And so if you guys watch these guys at all, the Mythbusters would always take myths of some kind, and this is one that they happen to do, to see, if we launch a bullet or fire a bullet out of a gun or drop a bullet at the same time, will this one or this one hit the ground first, right? And so I think I had this in the other PowerPoint as well, but I want to show it to you now because if you haven't seen it, it's worth seeing. And it's not very long. I have the shorter version of this.
Good grammar and spelling are important. But if you want to write essays that inspire,
You guys hear the sound?
messages that forge bright.
You do? Okay, I don't. For some reason, my AirPods stopped sound, apparently. I don't know why. Beginning of class, but they stopped working.
What you got there?
This is a good one. Picture two bullets, each exactly the same distance from the ground, each released at the exact same second, except one bullet up to the
experiment states that both bullets will hit the ground at the same time.
Based on what theory?
Based on the theory that the bullet that's fired from the gun has no rims on it, no lip. Thus, gravity has the same effect on it as it does on the dart bullet, and thus they hit the ground simultaneously.
Adam lays down a runway of white paper so the high-speed camera will clearly see and measure both bullets at the same time, in the same place, and in the same shot. All we need now in the drop zone is Jamie's draw quick, so the boys can take a shot at physics history.
All right, so you ready to do this for real?
I think we'll hit it on the first shot.
Really?
Oh, yeah.
You never make predictions. That's awesome.
Bullet drop versus fired. In 3, 2, 1.
But from 360 feet away, the boys can't see exactly where the fired bullet landed.
Let's go see where it hit.
So Adam takes a one-wheeled ride down the room to check out the drop zone.
Wow.
And the results are simply ripping.
Can't get much closer than that. Oh, I can't wait to see the high speed.
Adam analyzes the high speed and crunches the numbers.
So you see the free fall one hit the ground a little bit before the other one in slow motion.
6. Dude, the difference is 39.6 milliseconds.
Which means it's less than the human eye can make out.
So after days of brain-teasing tests, the Mythbusters can claim a world.
So what they have here is they have an electromagnet. That's why they have these wires that run all the way the length of the warehouse. So when the gun is fired, the electricity running to the magnet that was holding the bullet, right, stops, makes that trigger so that it falls at the exact same time. Now, nothing is perfect, right? And so there's, as he says, a 39.6 millisecond difference. Millisecond, right? Move the decimal 3 spots to the left, 0.0396 seconds. That's less than we can even realize is happening. And so essentially, and that all that difference can come into play with the mechanism because it's not perfect.
First for themselves. And a victory for physics.
Let me put 39.6 milliseconds into some perspective for you. When you go to the movies and watch a projected celluloid film on the screen, you know that that film's made up of individual images, right? What you might not have known is that it takes 24 of those per second to make up the film that you're watching. So each one is on screen for exactly 1/24th of a second, but you don't notice that because it's faster than your eye can register. Well, that 1/24th of a second is actually longer than 39.6 milliseconds. That's how close those two bullets were.
Right. And so, as he said there, that you watching a movie, right? The different images that come there is that difference between that bullet and the fired bullet and drop bullet is less than that, and we can't even tell that there's, you know, we're watching a movie. We think it's all one motion when it's not there. And so essentially, it doesn't matter how fast this thing is moving, it's going to hit the ground at the same time as long as it's launched from the same vertical height. That's the key. They're falling the same amount of distance. This is the best slide that I have, or I found. This is from the physicsclassroom.com, which is a very good reading. I don't think they have many videos, but it's a very good reading text about physics. But this shows you, you know, what if we roll a ball off a table and there's no gravity, right? So there's no force pulling it down. This is what the ball would do. It would just keep moving to the right. And now notice the distance between ball 1 to ball 2. It's the same ball, but at a different time period. The difference in distance is exactly the same. Why is that? Because once we launch a projectile, as I said before, the horizontal force is only in the very, very beginning. When you kick the soccer ball, you kicked it one time. When I push this ball off the table, I pushed it over here. I'm not running and pushing it over and over and over again. And so there's no horizontal force to make this ball speed up or slow down. And that's why we see the distance between consecutive balls the same, because it's moving with constant velocity, right? That's everything that we did in Unit 2 when we first started doing real physics. Here, well, what's the ball doing vertically? It's falling straight down, right? Or free falling, which is what we just did last unit. But this is its X motion, this is its Y motion, this is its resultant motion. And this is what we actually see. So here's the X motion, here's the Y motion. They're different types of motion. They combine to make this motion. It's the best slide, because what happens is when you see that if you roll a ball off the table, this is what you're going to see. Well, it's hard for us to mentally make a picture that this is really what's happening in the two different dimensions, because we're looking at this, right? And so this does a really good job of breaking it down. And then the nice thing with this is they put these little lines, because this, if you measure this distance, these vertical lines show you that the horizontal motion is constant, but you see these lines are getting farther and farther apart because it's falling and it's accelerating. So we have constant velocity, uniform motion. We have accelerated motion. They combine to make this, right? That's what a projectile's path is always going to be. And then this, again, this is also from the physics classroom. And so you got the cannon, it's firing horizontal. Now remember, these are called vectors. Those arrows, they represent the horizontal. Notice how the horizontal velocity is constant. You see that it's not changing, but Vy is changing, right? And notice it goes up by 10 because it's increasing by 10 meters per second every second, right? 10 meters per second squared. And so as it falls, the vertical velocity is changing because of the force of gravity, the acceleration of gravity. The horizontal velocity is always constant. It's got uniform motion, constant velocity. So there's a bunch of, on the physicsclassroom.com, there's a bunch of animations like this that kind of help you see some of the things in action. Now, we call these things components, Vx and Vy, right? Before we just had V. We didn't talk about being in the X or the Y. We just called it V, we just called it A, we called it D. But now we're doing two-dimensional motion, so we have to keep track of the two different velocities, the two different distances, right? Because when we look at where this thing lands, right here, Well, the horizontal distance is the distance from this cliff to where it lands. The vertical distance is this, right? How far it falls. So we're going to have a dx and a dy. And so we need to add some subscripts so we keep track of these things. Now, remember, we have an initial velocity and a final velocity. And so we're going to have a vox and a voy, a vx and a vy. So we actually have 4 velocities now, right? But we're doing 2-dimensional motion. So we've doubled everything in terms of distances, velocities, and accelerations. The only force, again, is gravity because we're always neglecting air resistance. Together, these components produce what is called the trajectory, right? The trajectory is simply the path that the projectile takes, right? I don't know if you've heard that word before. If you, we're in the military, obviously you would talk about these things if you watch military movies. It's probably not a word that we use very often in everyday language, but you'll see it, right? And the path is always parabolic, right? It's not a straight line because for it to be a straight line, that would mean both X and Y would have to have the same type of motion, right? But X has got uniform motion, constant velocity. Y has got accelerated motion. And so this is referencing the velocities. The horizontal component of the velocity is always the same in terms of how big it is and what the direction is. The vertical velocity is always changing. This should say constant, and I don't know why it does not. So I'll fix that, but I thought I fixed this already, but maybe I didn't save it after I fixed it. But it's always down, right? It's not changing. It's always down. This is always going to be, if in this case, it's to the right, right? It's moving to the right the entire time. This is always down because that's the way gravity works. Now, the last video I'm going to show you. This is a famous, kind of like in every unit we've done so far, there's always like that famous experiment or physics demonstration. And I normally do this in class. I have the equipment to do this. It's called The Monkey and the Hunter. Now, I know that this looks a little, in the 70s and 80s, we weren't very politically correct about things, right? I was in your shoes, so my physics teachers were showing me this stuff, and they were shooting the monkey and what have you. Now we're politically correct. We don't want to kill monkeys. Monkeys are actually very cute. I would not want to shoot a monkey. But that's and again, this started back in the 50s and the 60s, or probably the 30s and the 40s, or what have you. But the idea is we're over here and we want to, let's not kill the monkey, but shoot a banana at the monkey. So maybe we want to use a slingshot. And we want to get it to the monkey, but he's hanging from a branch. In the minute that I launch using maybe a slingshot, the banana, and I'm launching it horizontally, right? So here's a banana. We know that the banana is going to start to fall and follow this path. Any projectile is going to do that. Now, the curve might be less if the faster we launch this thing, excuse me, right, the faster it's going to get over here, the curve is going to be a little bit less and maybe not as pronounced as you see it there. But it's still going to curve down because gravity is going to pull it down. So the question is, if I launch a banana horizontally and I shoot it so it's fast enough to go this distance, but the minute that I launch the banana, the monkey gets scared and he drops, right? Will the banana reach the monkey, right? So think about that for a minute. This is a little, I'll show you the initial part of this video. Where'd it go? Here we go.
This is the checkers game where grandson and granddad will bond. This is the kitchen.
He sets the stage for you.
Now in this video, I'm not 1 minute suggesting that this is a good thing to do. So let's imagine this was a long time ago in a place far, far away. And what we have over here is a guy who's pretty hungry and he loves a taste of monkey meat. And this thing is quite a famous example, and it's called The Monkey and the Hunter. So here's the scenario. What you have is a hunter with a gun, or in this case an arrow, and they're going to hunt this monkey. They want to basically shoot it through the head so they can eat it. Now, this monkey's up a tree. This one, the hunter in this case, is on a bit of a hill. Now, the question is, when they fire their arrow, and this monkey is super sensitive, and as soon as it hears that arrow being fired, it's going to jump out of the tree, so it's going to drop down to the ground and run away. So, which way does this guy fire? Does he fire up so that the arrow goes up in the air and then hits the monkey at the bottom? Does he fire directly at the monkey, even though by the time this kind of leaves, the monkey already starts dropping to the ground? Or does he aim at the ground, so by the time the monkey hits the ground, the arrow hits the monkey? So, 1, 2, or 3, make your choice now.
So think about that. You want to aim, no, you can't see it.
Good.
Do you want to aim above because you know that the arrow is going to fall, right? But remember, he's going to fall at the same time. Do you want to aim right at him, or do you want to aim below him?
Choice, but was it correct? Now, this is the thing about the motion of an object, like a projectile, and about the independence of both the horizontal components of velocity and the vertical components of velocity. And in actual fact, the way that this arrow should be fired is completely horizontally, aiming at the monkey's head in order to kill the monkey, so he's got some dinner for him and his tribe later. Now, the reason for this is that as soon as the arrow leaves the bow, the monkey's going to start dropping to the ground. And this is going to have an acceleration of 9.81 meters per second. The arrow is also going to start dropping to the ground at 9.81 meters per second. It doesn't matter how quickly it's doing it. This could be going fairly slowly or incredibly quickly, but its vertical component of velocity is going to increase at the same rate as the vertical component of velocity of.
So this is the idea. Same with the bullet that's dropped or fired. Gravity's acting on, the force of gravity is pulling down on them with the same acceleration rate, and they're both falling from the same vertical distance. They're launched at the same time. They're going to fall the same amount every second. So that's why he wants to aim right at
The monkey. And that means as the two things are moving, which is actually quite hard to do, what we find is that the two things drop to the ground at the same point, and that means the monkey will be shot in the head and will die. Maybe not the most sort of PC way of looking at it.
All right, so that's the scenario. Now, what I would normally do, again, I have a setup, so I'm going to keep it there because I found a guy that basically he made the video for the teachers, but he did the same or very similar setup to
I'd like to talk to you about a legendary
what I would do in class.
called the Monkey and Hunter. It's legendary because not many people have actually seen it work, but it's one that's really worth doing if you're looking at projectile motion with your students. Now, you can buy specialist equipment for this, but I'm going to show you how you can do it using bits and pieces that you can find lying around in most school science labs. Now, the monkey is just a tin can, and it's hanging from a tree, which is an electromagnet made out of a transformer coil.
Same type of setup they had for the bullet.
The circuit is completed across the lab using the longest wires you've got, because it's much more impressive if you do it across a long distance. And it's connected by a very thin piece of foil here in front of my gun, which is just a hollow tube, which I'm going to use like a pea shooter with this plastic ball. You can use a marble or a ball bearing or any other similar setup. And the idea, of course, is that when the ball passes through the tube, it breaks the strip, disconnects the magnet, the monkey falls, and miraculously the bullet hits the monkey. Now, it's a fairly straightforward setup. However, if you've ever tried this, you'll know that things don't always go to plan.
It's very tricky to get set up to make it work initially the first time. A lot of timing.
I'm not doing it again. Now, believe it or not, it's not the aiming that's the problem here, because with this setup, you just sight it down the tube.
Right, so see how he's aimed right at the
What I
monkey.
think I was doing wrong is that every time I use the tube, I was wobbling it slightly so that the aim was thrown off. Now, I could have fixed that by perhaps using an extra clamp here.
That would have
or
been a good
using
idea.
Mechanical shooter that ensured a reliable projectile every time. There are some other problems that you'll probably encounter. For example, sometimes the foil doesn't break, so it's really important to use a very thin piece of foil. It is quite fiddly to get right, but it's really worth doing for the impact on your students.
So notice how it's falling, and boom, it hits right there. They fall the same amount, right? It falls the same amount, but it's moving horizontally, and he hits it. And he's very excited because it is exciting when it works. It's very frustrating when it doesn't work. So you'll see a lot of multiple choice questions with that. Again, that idea, same as the bullet fired and the bullet dropped. They're launched at the same time from the same height. They're going to fall the same amount every second. How much every object falls every second from our equation is, remember the D equals VOT plus 1/2 GT squared equation. How much an object falls is 1/2 GT squared, right? Because if the initial velocity is 0, what's left? 1/2 GT squared. So whether it's the ball launched horizontally, moving in X and Y, or the monkey falling straight down, they both fall 1/2 GT squared every second. And so they fall the same amount every time. And as long as he sights this exactly at the monkey, right, and if he blows harder and it gets there faster, he hits it up here. If he blows slower, so it doesn't go as fast horizontally, he hits the monkey just farther down, but he's still going to hit the monkey. So there's a common misconception too, when you're in a plane and they're throwing something out. Maybe a lot of times that people do this stuff to feed animals, like out in the West where you have a lot of land, because otherwise you'd be driving around for hours to get the cows or whatever, livestock you have food. So they use planes to drop it, right? Or if you watch World War II movies, right, they had physicists that would have to figure out, when do we drop the bomb if we're trying to hit a target? And so a lot of times people think, and especially I think if you play video games, especially the video games I played when I was older, if I was playing a game where I had to, kill a tank, you would drop the bomb because the plane would fly right over the target, and then you'd hit the bomb, assuming that it falls straight down. But it doesn't fall straight down, right? Because it's moving as fast as the plane is horizontally. And so you see how fast the plane is moving by the difference between these blue dots. And then, I don't know if that's red or green, sorry, but the projectile is moving the same horizontally even after it's been dropped, right? Because it's not going to fall straight down. Now, if you're driving down the car or driving down the road in your car, and you're not going to do this because we don't litter, but if you threw something out the window, right, it doesn't land right below where you dropped it because it's moving as fast as you are inside the car. So it actually follows a parabolic path as well, right? And it's a very common misconception, is that this projectile will be right below the plane. If the person dropped it right there, right over here, it's going to be right below their hand when it hits the ground. Again, we're assuming no air resistance, right? If with air resistance, we know that's not true. But I stole this from the physicsclassroom.com as well. All right, so now what are we looking at? Here's our equations. We have two separate directions of motion. We have to be able to separate the vertical and horizontal information. And this is key, the only information that is common to both is time of flight, right? Time doesn't have a direction. There's no X or Y with time. You can't mix X information with Y information. So when you read the problem, it's really critical. You guys have these skills because you've had years and years of English to dissect a paragraph or a problem to know, hey, that's a horizontal distance or that's a vertical distance. That's a horizontal velocity, that's a vertical velocity. But here's our equations. In the X direction, this is our only equation that we're going to use. Now, I kind of made it look a little bit different there. I don't know why. I did at the time. But again, for X direction, for X motion, we're going back to this equation, right? And now remember in the last unit, I said don't use this equation at all because we were dealing with accelerated motion, but now we're not, right? In the X direction, we have constant velocity or uniform motion. which means the horizontal acceleration is 0. Then we can use this equation, but we can only use it for the x direction, the horizontal motion. The good thing is the entire projectile motion unit, this is the only equation you use for the x direction. Now in the y direction, these are our equations. Now this should look familiar because this is exactly what we just used for the whole free fall projected up and down unit. We only used these 3 equations. They're the only 3 equations we're going to continue to use. But now what we do is we just want to put subscripts because we can't use this equation for x, right? We can't use this equation for x and we can't use this equation for x, right? And in vertical motion, we know that the acceleration is due to gravity, right? -10, negative because it's down, but 10 is the value, the magnitude. And so the horizontal motion is constant. The y motion is accelerated. And so we're combining the 2 units. That's what we're doing, is we're looking at something that's doing both of these at the exact same time. So it's the application of these equations when we solve problems. And I think we're going to have enough time to do at least one quickly, maybe 2. So like I said, what I did was I made the homework shorter. So we'll have a couple smaller ones, like with 4 or 5 problems instead of like what normally I would have is like 8 or so. And then we're not having a quiz until next Friday. So we'll have a bell work next Wednesday. We'll do a couple more problems and then you're going to do an activity of some sort. Now, I think we did a problem like this with free fall. It's a popular physics problem. Why? Because it happens, right? Especially if you play sports and you're out on a field and the geese especially are flying north or south, that's always a worry, right? I've spent years on a football field and I coached lacrosse for a long time and I coached baseball for a long time. So it's always a worry when geese fly overhead that you're going to get hit. You know what I mean, right? So this bird is traveling at 20 meters per second. I don't know if he wants to, but he's going to hit the waiter that's 10 meters below where he's flying. In order to hit the waiter, we know that if he goes poop, it's not going to fall straight down, right? It's not going to do that. Right? It's still moving at 20 meters per second. And so it's going to follow this path. What is this distance, right? We want to know, in order for that to happen, what is the distance from where he is now to where the waiter is? Okay. Now, when you're doing these problems, you have to be able to look at the problem and figure out what is X and what is Y. All right, you know what? When I use annotation, it doesn't do this. So I'm going to use annotation. All right, so for the X direction, what do we know? Well, we know that the bird is traveling at 20 meters per second. Right? And it's constant. So you could write Vx or you can write Vox. It's not going to change. The horizontal velocity is always constant, which means, because of what I've said, the horizontal acceleration is 0. Right? That's what allows us to use this equation for the X direction. The X direction only. What else do we know? Well, we know that in the Y direction, it's going to fall 10 meters. Again, down is negative, right? This is positive. This is negative. Again, you can make down positive, just like we did with free fall, if that's what you want to do. Now, what about its initial vertical velocity? Well, here's the key. When we get into angle problems, right, this is X, this is Y. In math class, you guys make this 0, right, and you make this 90. So when we do these types of problems, we do the same thing. He's flying, this bird is flying horizontal. That's an angle of 0 degrees, right? An angle of 0 degrees, we use theta to represent angles. I don't know what your go-to variable is in math, but in physics, it's theta. So it's 0 degrees. That means it's a horizontal launch projectile, right? Which is all we're doing right now before we do the angle ones. So because of that, because he's flying horizontal initially, the initial vertical velocity has to equal 0. right? Just like free fall. When we did free fall problems, what did we say? Initial velocity is 0. Acceleration is equal to g. These, again, these were our two go-tos, right? Our two values we automatically know in free fall, and then we just needed one other number. Well, we still know those numbers. And so these two things and this are true for the kinds of problems that we're doing right now until we start making angles. So the only things that can change is Vx or dy, or what are we trying to find? Our unknown, what is dx? This, or this are the only things that are going to change in these kinds of problems. So one of these three things is going to be the unknown. Now, what's the one thing that's missing from what I've written down? Well, time, right? Time is t. There's no x and there's no y there. So you're probably, the first step to any of these problems is going to be to find time before you can find dx. Okay, and again, remember, time is the one thing that can go between our x and our y equations. So now, so this is in my x direction. Okay, that didn't work. This is in my x direction. In my y direction, I have those three equations. But what you're going to find out is that you're going to want to use this equation for almost all of the problems, especially for what we're doing right now. In the next class, I'm going to show you why we would want to use the two Vy equations, right? So you can start out every projectile motion problem that we're doing right now with these two equations. This is the only one for x. This is for y. All right, so what are we trying to find? Well, we're trying to find dx, right? So let's solve this equation for dx. That means I'm going to multiply both sides by time. So do we know this number? We do, right? It's 20. Do we know time? Well, we don't. So we have to find time. This is why we're going to use the y equation to find time. And this is how every problem goes whenever time is not given. If your unknown is something is this or this, then you're going to have to use this equation to find time first. If your unknown is dy, then you're going to have to use this equation to find time first so you can plug it in over here, right? So you're going to have to use a combination of the two equations. Now, looking at this equation, what does this equal? Well, because he's flying exactly horizontal, this is equal to 0. Now, when we multiply 0 times anything, what do we get? We get 0, right? That whole thing is 0. So again, just like when we did free fall, right, we had this result. All we're doing is we're adding a y there to make sure we keep track of the different distances, dx and dy, right? Because this is dx, what we're trying to find. This is dy, that 10 meters, right? That's dy. Now, we're going to use this to solve for time. So what did we do? We multiplied both sides by 2. We divided by g. It's squared, so we take the square root, right? You've done that many times now. 2 times negative 10. Now, why do I make it negative? Well, because down is negative and it's falling 10 meters. G is also negative, and I didn't mean, sorry, I was thinking a couple steps ahead. That should be meters. This is meters per second squared. Right, the 10s cancel, the negatives cancel. It's the square root of 2. The square root of 2 is 1.4 seconds. That's my time. That value of time gets plugged in right here, right? It's the same time. It's moving this way and this way at the same time. Time has no direction, so we can do that with time only. And you should get, what, 28 meters. Right, the seconds cancel, we're left with meters. And so the distance, when the bird is here, he's got to launch that or drop that 28 meters away from him if he wants to hit him. Questions on that? Okay. Well, I know we only have like a minute or two, but I'm going to show you one more. And if you got to go, you got to go. That's fine. The homework is, like I said, a worksheet on this, which if you can't see it yet, I'll make sure you can see it when I publish it. Oh, I forgot you have to get rid of when annotate. I don't like that part of this that you. But I want to show you this problem only because it solves it. There's very few varieties of these problems. There's actually only 3 different ways these problems can go. This one does it a different way, and I want you just to see it real quick. So I'll kind of go a little quicker, so that way you're not late to your next class. Because I know you have a long walk. Right, so Billy Bob's standing on this bridge. He's kicking stones into the water. So imagine here's the bridge. Here's the stones. Here's the water. He kicks them, and it's going to go like this. He kicks them with a horizontal velocity of 5 meters per second. It lands in the water 7.5 meters away. So sometimes it's going to give you that idea of horizontal, so you know that's X, but maybe it'll call it the range, right? So we know that this is 7.5 meters. We want to know what is the height of the bridge. What is dy? Right, so what is dy? Well, what else do we know? These are the values given. We know VOY is always going to equal 0 because the angle is 0. We know that AY is equal to G. We know AX is equal to 0. Okay, so that's what's given. So now again, you want to know the height of the bridge. Well, how do we find height? Well, that's a vertical value. So you want to start out with this equation. In order to find this, what do we need to know? Well, we know this is 0, so this again is all going to be 0. We need to know the time, right? Because, excuse me, the Kettle Run Bridge is on the Earth, so we know that's -10, but we need time to continue. So that's why you need to then look at the X equation. This is the X equation. It's the only X equation we're going to use. To find time, we need to know these 2 values, and we know these 2 values. So I'm going to solve this for time. Right? Because I know dx is 7.5 meters. I know vx is 5 meters per second. Right? 7.5 divided by 5 is what, 1.5 seconds. Right? Pretty basic. We're just dividing 2 numbers that are given, but that value of time can go right here. And now we can substitute that in. 1/2 -10 1.5 seconds squared. And what do we get? We get a negative, because that's negative, it's falling down. 2.25, 22.5, half of that, 11.25 meters, right, is how far it falls. What is the height of the bridge? The absolute value of that, right? Heights can't be negative. That's the height of the bridge. So what we did was we used the fact that we can calculate how far the stone falls to know where it started. So that's the other kind of version of a projectile motion problem.